Assalamu alaikum. Today we will present our AICD project named Design of a Class A Common-Emitter RF Power Amplifier for the 433 MHz ISM band. Here's our project outline: abstract, introduction, design analysis, design methods, simulation, demonstration, and finally novelty, future work, COPO, and references. Our project abstracts here: design a class a common emitter RF power amplifier. Target frequency is 433 MHz, and we will use inductor based AC power flow and an impedance matching network for stable operation. Our project will perform in Cadence Virtuoso, and our project introduction we will use ISM band for popular for license-free short-range communication. RF power amplifiers are as critical in wireless systems and used to boost signal strength. And we will use class A common emitter power amplifier. Here's our project identification of scope. Topology common emitter, frequency 433 MHz, gain 10 dB, and power added efficiency 5%, saturation power 17 dBm, and technology we will use GPTK090. Here's our project literature review. First literature, Isa Kokakerin, Istanbul, 2011. In his BSc thesis, Kokakerin explores RF amplifier design and 433 MHz class A topology. We mainly take our main circuit from this literature. After that, we focus from the next literature, mainly RF amplifier target 433 MHz ISM band, and after that literature we mainly focus load line theory, matching network design, and efficiency. Here's our problem formulation, design problem formulation. Amplification goal was 10 dB gain, 17 dBm power saturation, and power added efficiency was more than 5%. Design technology was class A common emitter topology for linear amplification suitable for ISM band, and biasing for biasing and stability we used mainly inductor based biasing for low noise and stability, and for impedance matching we use and ensure input output matching to a 50 ohm system with input return loss minus 10 dB and output return loss minus 20 dB. And we simulate this whole circuit in Cadence Virtuoso, and for matching network we use QUCS Studio.
Assalamu alaikum everyone. My name is Ilyas Ahmad, ID 68. So let's discuss about the design method of our project. So for designing this amplifier, first we need to select a suitable circuit that match all our requirements. So we review different types of paper, and then finally we select a suitable circuit that can meet our requirement. Then we simulate the circuit in Cadence Virtuoso, and we all know that for designing an amplifier, Q point is very important. So that's why we then add adjust the Q point of our circuit. Then we simulate a S parameter in Cadence Virtuoso and extract the X parameter from our circuit. Then we need to design matching a network. For this purpose, as my groupmate said earlier, we use QCS Studio. Here we input S parameter and got our relevant matching network. Then we simulate our circuit with matching network, and finally we adjust and tune different parameter of our circuit to get all the desired requirement. Okay, so let's discuss detail about the design simulation and implementation demonstration of our project. Here's the calculation of Q point adjustment. We take VDC as 10 volt and assume that biasing current IC equal to 40 milliampere. So we get our our emitter resistance equal to 25 ohm and collector resistance equal to 100 ohm. And for getting base resistance, we are using basically DC sweep, and from DC sweep we found that for 40 milliampere current we need 1.187 K base resistance. So here we can see finally our circuit is Q point adjusted. Then here's the final circuit without matching network. We can see we use this circuit to for meet all the requirement. Then we simulate S parameter, and here we can see the S parameter magnitude and S parameter phase of different four S parameter of our circuit. Then for here we can see QCS Studio. In QCS Studio, we input all the S parameter phase and magnitude, and finally we get this matching network. So here all for me. Next part we'll discuss by my another teammate.
Assalamu alaikum. This is our amplifier after integrating the matching network. The purpose of this network is to maximize power transfer by matching the source and load impedances at the desired frequency, which is 433 MHz. Here we have the S parameter simulation. After integrating the matching network, we can see several values of S parameters such as S11, S12, S21, and S22. We can see that the S21 value, which is the forward gain, is 10.1118 dB. Here we can also here we can again see that the S21 value is 10.1118 dB, which is the forward gain actually. It means that how much power is transferred to the output from the input. Here is the input reflection coefficient, which is S11. We can see that the value is minus 33.508 dB, which represents a better impedance matching and less power being reflected back into the source. This is our power gain analysis. We use S parameter simulation in Cadence, following this configuration to measure gain across frequency. This is our output, which is the power gain. We have obtained 10.1138 dB, which is higher than our target value of 10 dB. This confirms the amplifier meets performance expectations. Next, we move on to the preset analysis. At first, we examine the harmonic content in the output voltage. As shown, the fundamental frequency component is dominant, which is 1.46871 volt, and rest of the higher order harmonics are negligible. After that, we check the harmonic content in the output power. Again, we can see that fundamental frequency clearly dominates. we can see that output power of 10.6935 dBm at the fundamental frequency and minus 24.8429 dBm at 866 megahertz, and the rest of the harmonics even show the lesser, much lesser value than this one also. We performed harmonic balance simulation in Cadence at the fundamental frequency to analyze the power output versus power input and eventually find out the PSAT. Here is the P output versus P input graph. Here we can see that at the input power 6.46 dBm, the P1 dB is 18.013 dBm, which is very close to PSAT. Next, we move on to the PAE analysis, which is power rate efficiency. Here we can see the PAE simulation analysis. Here we can see that we have simulated in Cadence at 433 megahertz. As we have stated earlier that the fundamental frequency dominates, so we have simulated at this frequency only. This is the PAE simulation. Here we can see that the PAE value is 7.52% at 6.46 input power, which we have already found in the PSAT analysis that at that value of input power, we had got the PSAT 18.01 dB, and our requirement was PAE needs to be greater than 5%, which meets in this criteria.
Assalamu alaikum. I'm Shonamid Rifat, ID 2006116. Besides Cadence tool, we have also calculated manually PAE. This is the circuit we have modified for manual calculation of PAE. We just replace the input port with a resistor 50 ohm and a AC source. We have replaced the output also with just a resistor. After modification, we have simulated this circuit for transient analysis. We have plotted Vout from which we can get output power, and I input, current input, from which we will get input power. As we can see in the graph, output voltage peak is 1.46 volt and input current peak 4.29 milliampere. We have also inspected the input and output impedance. As we can see, input and output impedance from ZM1, which is 49.9975 ohm, which is almost equals to 50 ohm. The input impedance is mentioned in this figure, in this circuit. As you can see, the input impedance is calculated as before. Here is the calculation of input power and output power. Input from the previous plot, we have observed that our input current is 4.29 into 10 to the power minus 3. We have converted it into RMS by dividing it with root over 2, and we have simulated the circuit for 500 millivolt, from which we can get the input RMS voltage. From that we can get input power is 1.0725 milliwatt, and also we can get output power from the output peak voltage converted to RMS, which is 1.46 by root 2 square by output resistance 50, which is 21.316 milliwatt. We have performed DC simulation to get the DC power from the DC source. This is the circuit for DC simulation. The DC power is calculated in this slide. For DC voltage, we have simulated the circuit for 10 volt, and we got the DC current 30.5303 milliampere, from which we can get the DC power is 305.033 milliwatt. We can calculate PIE from the output AC power minus input AC power by total DC power, which is 6.63, which satisfies our requirement is 5%, and also supports the Cadence simulation, which indicates 7.5%. This is a novelty of our project. From the novelty aspect, we have introduced inductor to restrict the AC power going to the DC sources. It reduces noise and enhances our performances. We have optimized the system for 433 MHz ISM band, which we have also impedance matched. We have also devised an impedance matched network to get the maximum power efficiency. We have simulated this circuit in Cadence Virtuoso, which reflect the practical parameters also. This system is a highly low power and power efficient design. As you can see, the comparison between target and our HEV specification. If we see that our target was 433 megahertz, and we have devised the circuit for 433 megahertz. All parameters are optimized for this frequency. Our gain was 10 dB, and we achieved 10.1138 dB. Our power rated efficiency was required 5%. We have achieved 7.5%. The saturation power, which was required 17 dBm, we have attained 18.01 dBm. Our technology required was GPDK 90 or TSMC 18. We used GPDK 19 for this project. Future work may be in this circuit, integration of advanced modulation techniques, optimize the circuit for multi-stage amplifier for better gain, thermal power efficiency, thermal stability can be introduced to the circuit. Here's the reflection of our individual and team work. We just got 6 weeks for this project. First week we have spent for literature review and background. All member was involved in this. Then we designed the circuit from the literature and simulated in Cadence Virtuoso. After that, we devised how we have introduced how to extract S parameter and device matching network in QUCS Studio. Then we optimize the system for our desired frequency. Testing, robust testing and validation process was followed for this amplifier. After that, we have finally presented and documented all the project. Every member was involved in this process. I have the external links added for the external stakeholders. Our COP alignment also mentioned in our presentation, where as you can see that application of semiconductor which is made in this project, designing of solid state, we have performed this for BAP and BBGT. So it also met demonstrating our teamwork network, our team work efficiently and actively in this project. Then applying our design for analog integrated circuit and communication design synthesis, which was also met. The references are mentioned here for our literature review, our circuit sources and others to go through. Thank you, everyone.